Hello there. So, welcome again. And we have covered quite a few modules on using the KiCAD, which is a free or an open source circuit design software offered by the community. And we have got a few useful circuit designs using the KiCAD and the SPICE. With that, specifically, we explored the filter, second order active filter design. And in that series, as you can see on your screen, we covered in our previous module the design and analysis of second order active Sallen-key filter, specifically a low pass circuit. So we got two sub circuits of the Sallen-key topology, the low pass filter without gain and with gain. So here you can see that operational amplifier has been configured using the negative feedback and through means by means of resistor R3 and R4. We configured this operational amplifier in a non-inverting amplifier mode, and then we have got R1, R2, C1 and C2 to provide the filtering network of impedances. And together this circuit acts as a second order active Sallen-key low pass filter with an amplification gain. And if we short this resistor R3 and if we open circuit or remove this resistor R4, this amplifier takes the form of voltage follower circuit with a feedback directly connecting output back to the negative pin of the input. So we also covered that. So in that case, the circuit of op-amp behaved as a buffer between the output and the input signal. So here is an input signal, and finally here comes the voltage that is basically becomes an input to the positive pin of an op-amp. Now, in this circuit, I am going to do some adjustment. Specifically, I'm intended to swap the position of the resistors with that of the capacitors. So, in other words, I want to replace the resistors with the capacitors and vice versa. So, I will replace the capacitor with the resistors. And with that, I want to see the response of this circuit, how this will behave. As I don't feel a need now to explain you again why this specifically IC, that is the special part from the manufacturer TLV9062. You can use any other operation amplifier, no problem. What is the purpose of power underscore flag? Why we have dual power supplies, 2.5 volts each? What is the significance of this power flag? What are these? These are the positive and the negative voltage supply pins of the operational amplifier. So what we can see here, we got this amplifier, and I have covered all these details in our previous model. So if you're new to this module, if you are seeing this first time, we encourage you to refer back to all of our earlier models in order to have a better and good understanding of this particular topic today. So let us one by one analyze. So what I'm going to do, I will just break the connection at this point and at this point. I will also break the connection at this point and at this point. I would also break the connection right here and right here. And finally, I want to break the connection at this point. So, and at this point as well. So with that done and said, what I'm gonna do, I will take this capacitor right over here. That is my C1. And this resistor, I will take it at this position right here. Then this resistor goes right here and this capacitor comes right here. So obviously I'll right click and then click transform section selection, rotate it clockwise. Similarly, this resistor, I will right click on it, transform selection, rotate clockwise, and then I will just drag these components at their positions. So this capacitor becomes here, goes here, and then I will connect all these components through the wires. So you can see that I am slowly swapping the position of the resistors and the capacitors into my circuit, transforming the originally second order active low pass filter using Sallen-key topology into some other form of a filter in a moment, not in a moment, but in a time to come. As we progress, we are going to see what kind of behavior this is a filter that I can reveal to you. This will behave as a filter. So we'll see how and what kind of behavior the circuit will exhibit, what kind of filter response specifically. So right now you see we have got input signal where DC amplitude is set to 0 volt. Here you can have 100 millivolts. So let me show you like 100 millivolts. You can change all these parameters. Let's say the frequency is 500 hertz, AC is equal to 1 volt. So depends on what kind of analysis you shall perform. DC, AC, or transient, you can use all these parameters. So we'll start with the DC operating point, but we have done and covered that in a previous module with the low pass filter. So I will skip that. Rather, I would be interested in showing you the two forms of the analysis. One is the AC analysis, and second is the time domain analysis. So with all that said, I will just click the save button, and then I have performed the ERC of it. Remember, I am setting the gain using R3 and R4 to be, the gain will be 1 plus R3 over R4 in a non-inverting fashion. So the gain is 2. So output will be twice to that of the input signal. That is what I want. And 20 log 2 in decibel will be my gain. So what I'll do, I will just hit the simulator button. I will then click here new analysis, and then I will choose DC operating point. That is just giving me the voltages and the currents into the circuit. Rather, I would skip that because we have done that in a previous model. So I will click small signal analysis. I will say take 2000 points, start frequency 1 hertz, stop frequency, let's say 100 megahertz. Okay, 100 e to the power 6. Click OK. Once that is done, I have got these signals. VO, that is gain, and VO of phase. Gain and phase of the output. VO is the output I am interested in plotting. So before that, I will hit this run simulation button. The simulation has started and it ended very quickly. Then I will be interested in seeing the response of the filter, and very clearly I can see that at the DC or at the very small frequency, I have an attenuation of minus 153, and it increases up to minus 9. And at around 10 kilohertz right here, or 8 or 9 kilohertz, I reach a gain of 1, that is 0 dBV. Okay, so that's the cutoff frequency set by the passives, which are R and C, R1, R2, C1, and C2 of my circuit. So on the schematic, we have values of those components. Just use the formula omega equal to 1 over RC will give you theoretical calculation, which will match here with the frequency simulation of about 9 kilohertz, something like that. And after that, you've got the flat band. So this is called as flat band or pass band of the filter response. So this clearly indicates you are dealing with a high pass filter. You have designed a high pass filter. So after the cutoff frequency, where your input signal frequency is greater than large, very, very greater than the cutoff frequency, you have a constant gain of about 8 dB V. So let me zoom in this portion right here. So it's a kind of band pass response, but we have to tune in, then we can understand and adjust that. So you see gain of 6 dB. So in a magnitude, you have a gain of 2, and 20 log 2 will be 6 dB. All right, if I'm correct. Correct me if I'm not. So I will right click and then fit on screen. So here at very high frequency of more than like 8 megahertz, then my gain drops again. So if I want to take care of it and see if I can do something about that, because I would want all the constant gain for all the frequencies right here. That's the ideal behavior of a high pass filter. So what going to do is I will just click here add tune value, and I would like to play with let's say this capacitor. So instead of 2.2 nano, I would try to use the only one value of that capacitor. Like let's say I want to fix it. It can go up to 4.4 high and low is 1.1. So I will set it 1.1 and see if my behavior changes here. No, in fact, it degraded at the earlier frequency. What if I try to go up and look at that? Little bit improved. So what I'll do, I'll fix it to 1.1 nano and I will just click it again. And then maybe I would like to play with this register right here. And I come back here, I can tune the value of R1 now. So let's say I have it like 5K, but now look at this. There is a resonance here. There is a quality factor at this frequency. Your gain is signal is getting amplified by the quality factor value. So I don't want that. So instead, let's say I can just keep doing it, keep tuning the value and see how my response of the filter improves. So I keep it like, let's say, here I want to keep it 10K. That is okay. And little bit this kind of response is okay. So here it is. So what if I want to, let's say, play with this value of resistor R2? Maybe I can do that, try that. So I have got R2 value and see if I tune it to 5K or maybe increase it bit more, increase it to 20K, but that's doesn't make sense. So let's say I set to 10K maybe. So here it is 10K and that's it. So what I can do is try to play with these values R3 and R4. So let's say R3 is there. And now with R3, I can see that maybe little bit decrease it and see if the filter response improves. Not really, but maybe increase it a little bit. But there I am getting the response of here I have a resonance which I don't want, right? So for example, so this is how you can see you are able to tune in the response of the filter. But this is like 10 megahertz. After 10 megahertz, your gain is dropping down. But so far, you can see that it can filter with a constant gain amplification. All signals all the way from like 20 kilohertz up to 10 or 8 megahertz. So that's good. Okay, so we'll keep it like this. How about we run the transient analysis? So let me uh, or maybe let's say I want to run the transient analysis. So with that, I will choose the time domain. Timestamp is like 1 micron. Final time, let's say 1 millisecond. Why 1 millisecond? Because the input signal frequency is just 0.5 kilohertz. If you see the schematic, okay. Initial time, I skip it and click OK. Once that is done, I'll hit the click button. On the schematic, I have VO. I am interested in plotting VO, that is the output and the input. So let me show you the input is a 1 cycle. So what I'll do, I want more cycles to see. So instead of 1 milli, I will say 10 milli. And then click again, great. So I'll have like 5 cycles here, 1, 2, 3, 4, 5. That's my input and output is getting attenuated. Why? Because this is a high pass filter for low frequency of just 500 hertz. I don't have any signal is heavily attenuated. That is clearly understood. So what I'll do, I will just press escape button to get rid of that bar there. Instead of 5,000, I will say 5 kilohertz. So remember our cutoff frequency was about 8 kilohertz in the frequency response. Or let me show you, you can see that again here by clicking here. Here is the cutoff frequency. So more than 10 kilohertz, uh, you have a higher gain, right? Gain of 2. So go back and now simulate again and see if your signal will improve. Yes, it got improved, but your signal is output in blue is still attenuated, right? So now what I'll do, I will just adjust the 10 milli. Instead of 10 milli, I will say 5 milli. And now click run simulation. So that's much clear, better, but I have 100 millivolt peak signal and I get like 20 millivolt peak. And this is like, you see, this is like what is the response look like? There is a phase shift I can see clearly. There is like, there is a phase shift between input and output. Okay, so what we'll do, we'll just click come here and instead of 5K, I now want to use the 10K and see how the circuit will behave. So will the output be equal to input? And so faithful filtering, we'll see in a moment. Yes, it's quite close, right? So we have to apply even higher order frequency. So for example, let's say instead of 10K, I am interested in 20K now. And now we'll see how the signal will look like. So for a 20K, I got a very good response of the filter. So output is now bigger than the input. Obviously, there is a phase shift between input and output. So it's not clearly 0 degree phase shift or 180-degree phase shift. So that's because of the capacitors and that you have in the circuit and the op-amp behavior. But you can see now your input is 100 millivolts peak and output is like 130 millivolt peak. So it's still a big one, right? So you can try with different frequency and see the behavior of the circuit. What if I don't want an amplification gain, I just want to use op-amp as a buffer. So with that, I will see the frequency response and the time domain response. So what I'm interested to do is just use it as a buffer. So I will just click this, I will remove this, and that is what I want. I don't want it to be use it as a like, okay, so it is just I'm connecting it output back to the input or negative pin of it. So using it as a voltage follower, output voltage will be voltage at the input, that is at the positive input. So this is just a buffer. Additionally, it provides high input impedance and low output impedance. So now I've got 20,000 hertz frequency with a amplitude of 100 millivolt, and I will see what is the transient domain response will look like. So I will click the run button. Could not apply the tune values. Obviously, I have actually removed these two registers specifically in the feedback path. But now you see, uh, before that, I zoom in. What I shall do is I'm not interested in the tuning the R1 and R3. So R1 and tune C1 and R1. So let me show you what those C1 and R1. C1 is here and R1 is right over here. So let me zoom to the circuit. This is R1 and this is C1. So we have removed R3 and R4, R1. R1, R2 is there, C1, C2 is there. So what's the response like? Let's say I hit the simulation and now input is bigger and the output is smaller. So obviously, which makes sense because yeah, right here. So I have to first check what is the frequency response now. Remember, this is the frequency response when I use op-amp as a non-inverting amplifier, that is with the gain. Now I'm using op-amp as a voltage buffer or voltage follower. So I'll click the button and look at this. I have got exactly 0 dBV. That's a gain of 1 only because it's a voltage follower. Gain is 1. And the cutoff frequency is like close to 40 kilohertz. So when I apply that high frequency, I shall have the output is equal to input. So let me use it like 50 kilohertz. So we'll see that. With the 50 kilohertz, I will be able to see the input and output both ways. So for example, I'm not running AC response now, rather I'm interested in transient. So I click here, click the run button, and now both should be equal, close match. That makes sense. Output and input are equal. Look at this. Output and input are equal. What I'll do is click export current plot as PNG, type some name, save it in a folder you want. That's it. Also, the AC analysis looks like that. So just export current plot and say like this and okay. So you're saving this. So this is how you can transform and design your circuits with the high pass behavior. So that's the conclusion of our discussion on Sallen-key high pass second order active filter. Okay, so hope you found this module useful. You got to understand different aspects of this circuit. One more thing that you would be interested in doing, for example, you just run the transient analysis and you can see that that's your behavior of input and output. Zoom in, then you can click the new analysis, select the FFT. So you want to plot the fast Fourier transform of output and your input signal. You are very welcome to do that. Click OK. Once that is done, click the run button and then you see here there is a console window and then click FFT of input and then click FFT of output. So that's really a wonderful waveform. You see your signal frequency is about right here. Okay, you can zoom in this kind of plot. So at about 50 kilohertz, that's what you have applied here. See the screen, you have applied the signal frequency of 50 kilohertz and that frequency got passed at the output. That's a high pass filter response. And you have got the spectrum of 50 kilohertz as well. So click in here and then maybe right click and then fit on the screen. That's it. So you do one thing, let's say click here and be interested in having a different color maybe. That's it. Then file, export current plot as PNG and then say FS or FFT, whatever name, save it. That's it. Then what next you can do is come to transient and AC analysis again, run the button, click the run button. Once that is done, click new analysis. You are interested in the noise analysis. So measured node is output, reference node is optional. So leave it like that. Noise source. So which is your noise source? V5. Like I want to say that my input voltage noise source is V4 actually, input voltage source. So I will choose V4 here. Now number of points per decade, let's say 2000, start frequency like let's say 1 hertz and higher frequencies like 100 mega. Then click OK. Hit the run button again and your noise analysis has started. And you see that this is finished now. Once that is done, you've got two signals to plot in noise spectrum and output noise spectrum. So you are likely to plot the spectrum of output noise and the input noise. So you click here and look at this response. So you've got the noise spectrum expressed in volt per root hertz. This is in nanovolt actually, nanovolts. So it's like 315 nanovolt at the DC. That's the output noise spectrum. Then it decreases. It remains constant throughout up to 1 mega and then it's increasing. What about the input noise spectrum? So here you can just deselect that input noise is like 64. Well, that is it starts with like microvolt or millivolts. Just let me see that. Yeah, this is how. So, but the unit is a little bit confusing. So you can just let me know in the comment section. So let's say fit on the screen. So it is very high at the DC. So it's a kind of flicker noise at the low frequency. And then for higher frequency, it's a white noise as we can understand from our concept. So this is constant at very high frequency, right? From 10 hertz to, but at ultra low frequency, you have got the input noise spectrum. So that's how you can actually do that. Okay. So maybe you are interested, then you can do one thing, just click file, export current plot, then just give it some name, save it. Okay. What if you change the signal source? Maybe just change it instead of V4, let's say V1, and measured node is, let's say, V in, if you, and keep it V4, and we'll see if there are things that can change. So click OK. Your signal, your analysis is being performed, and a little bit wait, and then you don't really have anything. Okay. So we just ignore that. The earlier analysis was okay. So hope you found this module useful. You learned a lot about different analysis to perform design. You can play around the values and the design as per your specification. The second order Sallen-key high pass active filter. So till share it with others for wider reach. Till then, wish you happy learning. Stay tuned for more engaging content like this. See you.